I do have almost 30 years, and I've been doing everything from water resources planning through modeling, design, etc. And you can see my email on there if you have any questions later on that you would like to send to me. And with that, I'd like to get started. What we're going to talk about today is combined sewer modeling. And it's so tied into sanitary sewer modeling that I wanted just to explain a little bit about how this works. So back when we first started working and designing and laying out our streets and homes and businesses, we put one sewer in the street, and we connected our service laterals, which picks up our sanitary sewage, and we also attached our storm sewer to that. And what would happen is when we get a big storm event, the water would overflow out of a manhole or at an overflow structure into the river, into a lake, and it's called a combined sewer overflow, or a CSO. And the difference in a combined sewer system and a sanitary sewer system, or what we also call separate sewer system, is the fact that in a separate sewer system, the rainwater and runoff go to a different sewer, to a storm sewer, and discharges directly into the river or lake, and the sanitary sewer goes to our wastewater treatment plant and gets treated. In fact, my next slide shows an example of a community that has a combined sewer system. You can see the stormwater goes in during dry weather flow. This is from the Washington, D.C. area. The water goes to the Blue Plains Advanced Treatment Plant and gets treated and gets released. During wet weather flow, the water gets high enough and it flows out into the Potomac River. Another option that has been used around the country are deep tunnels. And here is an example of what we call an extreme wet weather flow from the Milwaukee Metropolitan Sewer District. And you can see that, if you look at my mouse, the storm sewer itself just discharges right into the river or Lake Michigan. The local sanitary sewer goes down and drops into the interceptor and flows to the treatment plant. And in an extreme event, if we have what we call an SSO, or a sanitary sewer overflow, the water goes into the river again. In the downtown area where we have combined sewers, you can see that the streets as well as the buildings are all hooked up, and the first bit goes to the collector sewer, and if it can't fit in there, it drops into a drop shaft and goes to the deep tunnel system where it's stored and later pumped up to be treated. If that gets full, then again we have a CSO, or a combined sewer overflow. You can see on this map where combined sewers are located, primarily concentrated in the Northeast and in the Midwest. We do have some in the Northwest area in Washington and Oregon. We also have a couple in California and a couple in Georgia and North Carolina. But for the most part, they're concentrated in the Midwest area and the Northeast. What happens with a combined sewer overflow? You get things like this, where surcharges and water can come out of a manhole cover, as you can see here. And then also with that, you oftentimes get basement backups and basement water in the basements, and you end up to cleanups like this. I am from Milwaukee, Wisconsin, and seeing kegs laying over and been damaged is just, kegs of beer, that's just hard for me to take. But those are types of things that we run into in combined sewer overflows. And what I wanted to talk a little bit about here is what the EPA policies are for combined sewer overflow. In other words, not just how to model them, but a little bit of the background for those of you who may not be completely familiar with combined sewers. So the EPA has basically 4 policies that they've implemented. First of all, they want a clear level of control for health standards. Obviously, when you have a combined sewer overflow, it's a combination of sanitary sewage, carrying fecal coliform and other nasty critters, and stormwater. It is diluted, but we want to know and that we get layers of control, a level of control to deal with that. The next 2 are very similar in the fact that while there's important to control the combined sewer overflows, we want to focus on a cost-effective way to deal with them. The idea of just spending billions upon billions of dollars isn't very viable, and so we try to phase it to accommodate the financial capability. And finally, we also have to deal with where does this water discharge to, and site specifically, what does it do? For example, a discharge into Lake Michigan would be considered differently than a discharge into a small creek or stream where the dilution factor still is applied. And to do this, the US EPA has created what they call 9 minimum controls. Those of you, like I said, who are familiar with combined sewer, you've seen these before, and I'm just going to spend a couple minutes to go through these. First of all, obviously, maintenance of these systems. We want to make sure that there aren't clogs in there that will lead to overflows. We want to make sure that the sewers are cleaned on a periodic basis and that the CSOs are functioning correctly so we don't get combined sewer overflows except during wet weather events. Another thing that we want to do is to maximize the collection system for storage. The example I want to quote here isn't from the US, but it's actually from Canada. Quebec City has managed to move their water back and forth from the east and west sides of the city to better deal with storm events that come in. So if something's coming in on the east side of the city, they can actually move water to the west side and therefore not have an overflow as quickly. Obviously, pre-treatment is critical. Anything that we can do for pre-treatment of CSO so that they're minimized, these impacts are minimized, are important. And we also want to maximize the amount of flow going to the treatment plant. And for example, it's one of the things I did several years ago with Gary, Indiana, where we redesigned the overflows to maximize the amount of water that we could get to the treatment plant, and then start working on the actual overflows themselves. They are prohibited during dry weather. So if there's no rain, there better not be any combined sewer overflows, and if there are, you have to explain what happened and why. And that goes back to the first one of maintenance, right? If it's well maintained, everything should be working correctly. We also want to control solids and floatables. So maybe some kind of a vortex separator or some kind of disinfectant could be applied to minimize the impacts to the receiving waters. And that goes right in with the next one, pollution prevention. And finally, we also want to notify the public so they're aware of when these occur and what impacts there might have to them. You'll see that, I see that quite a bit in Milwaukee, where maybe there'll be some beaches closed after a storm event where the fecal coliform are too high for safe swimming. And then again, monitoring the impacts to the current water that discharges to, and then how effective are our controls. The final thing that I want to talk about is the elements of a long-term control plan. And you'll see that these pretty much parallel what we just talked about, the 9 minimum standards. We have to take care of the combined sewer system, including modeling, which is why we're having this little get-together today to talk about that. We want to include the public in it. Cost and performance considerations are important. Once again, we don't want to break the city or county, whoever is responsible for it, the sewage district, to do that. And we want to have a implementation plan, an operational plan in place so that the water is treated and dealt with in a proper manner. So for example, if I have a treatment plant and it has a certain capacity, but I can get more water to the plant, maybe I can put in some kind of a storage device and hold the water and then treat it later, or hold the water and do some settling and then add it to the waste stream, which is called blending. There are all kinds of different things that we can do in that way. And finally, we obviously need to do some post-construction compliance work, make sure that everything is working according to plan. So why do we model? Well, basically, we want to be able to apply field and SCADA data, field data and model data to model hypothetical storms. Some of the things we want to accomplish with that is US EPA requirements. Typically for a CSO, it's 4 events per year on the average. And again, that depends upon kind of what region you're in a bit, and then meet the 9 minimum controls. And the last thing we want to do is to evaluate alternatives. What can we do to meet the requirements of EPA or even better them? So what we have, first of all, is a very simplified model. And our simplified model shows we have dry weather flow, which is sewage and infiltration, and we have wet weather flow, which is inflow and infiltration. In a combined sewer system, the inflow and infiltration is the heaviest part and typically add up to a much larger percentage of the flow than the dry weather does as compared to a separate system sewer. So what we have here is we have our hydrology, and we have rain falling on the surface. We have water that runs off fast. That's the water that's going to get into inlets and places like that. We have the slow response, which is water that's going to percolate into the ground and work its way down and maybe enter through pipe cracks and bad joints, etc. And when we start talking about modeling, we have to determine what do we want to do for subbasins. And typically in a combined sewer system, we look at modeling a combined sewer system with at least 2 subcatchments. Now in XP Swim we can have up to 5, but we'll want to do at least 2, where one will be basically everything but the roof drains, because typically in a combined sewer area the roof drains are connected. And one of the options we can look at is to remove the roof drain. So by doing this, we can actually route the water over the pervious area and then see what kind of reduction we can get, low impact development type of concepts. We're going to talk a little bit more about that as we go through the system. And the last thing we want to talk about is base flow, which is infiltration that's getting in. Typically it's fairly constant and maybe seasonally varied. For example, here in the northwest in Portland, Seattle area, you'll find that a 1-inch rainfall that would occur today has a completely different response than a 1-inch rainfall that would occur, let's say, in August, where in August most of the water would soak in. Today, more things are saturated and you get more runoff than you would in the summer. There are really 4 different types of modeling or routing methods that are available to us. We have the steady state, the dynamic, the 2-dimensional, the 3-dimensional. We're really going to talk about the second one, dynamic, but I just want to touch briefly on the 2-dimensional and 3-dimensional models. A 2-dimensional model allows you to determine what the impacts would be if the water would come out of a sewer system, combined sewer system, and dump into a small channel, overtop out of a inlet, overtop out of a manhole, and would run. You could model it as a bypass and see where that water would go. 3-dimensional models are primarily used for, let's say, a combined sewer system overflow, where it gets very complex hydraulically, and just doing the standard dynamic modeling isn't sufficient. So let's talk about steady state first. Steady state is basically Manning's equations or the kinematic wave, and you solve for flows. The data needs are very simple. You need the diameter and the slope. But there are limitations associated with the steady state model. Primarily, it doesn't do negative flow and backwater conditions well. It is valid for gravity systems and can handle simple pumps. It doesn't do surcharging very well either. You can see in some examples that even the cumulative peak flows become very disjointed when you run a model in steady state versus 1D. So XP Swim is a dynamic model. We do solve the full St. Bernard equations that you see here. The mass balance is the one I'm putting my mouse on right now. And that is at the nodes. And then we have the momentum equation, which is down here, and that is at the links. If we were to eliminate the first 3 terms, that's what the kinematic wave is, also looks like, in addition to the one we looked at, which was Manning's. What are the limitations of it? Well, before we do that, what are the data needs? Well, we need a little more information. We need conduit geometry. We don't use the slope. We actually use the inverts itself. And we need node rims and inverts so we can calculate what's happening within the pipe. Limitations, not really too many anymore. We do have model instability at some times, even though that's pretty rare today. I don't see it at all. Well, I shouldn't say at all, but very rarely. And we still do have to do some geometric simplification. For examples, in many combined sewer systems, we have increasers and decreasers in size, where over a period of maybe 5 or 10 feet, the pipes change from a 2-foot pipe to a 2.5-foot pipe, or reverse from a 2.5 from a 2.5 to a 2. Those aren't easily modeled. We have to model it really as just a transition, and because we are current limited, that is another condition that we have to be look at. So what are the components? Well, we have basically 3 flow components. We have domestic sewage, we have industrial flow, and we have storm flow and inflow and infiltration. And you can see the examples here: the home, the industry, and finally the inlet. Domestic sewage, where does that come from? Well, that's from the homes, commercials, institutional. How do we determine that? Well, typically we use the population, the land use, and the per capita employment. And this is how we do it in XP Swim. We can determine what our flows are. We can bring in up to 4 different units. We can use CFS, MGD, gallons per minute, gallons per day. And depending upon whether we use direct flow, unit rate, or census-based, we can do a full multiplication here. Basically, if you look at the census data provided, it's called Tiger data. That's going to give you, you can use the flow rate, the area, and the density to determine this. You can also use a peaking factor, which allows you to look at what might happen in the future. So you get done with an analysis and the client says, well, gee, what's going to happen if our population grows by 10%? Well, I can go right in here to the peaking factor and I can type in 1.1 and determine what that would be. I also have a unique profile, and it can be a daily adjustment as well as an hourly. If we look at this data here, you'll see that Tuesday has a multiplier of 1.25, and we have a multiplier of 1.8 at 5, 6, 7 in the morning. So our peak flow would occur on Tuesday at 7 in the morning. Please note that we start at 1 a.m., so this is actually midnight down here. So it's 1, 2, 3, 4, 5, etc. I can have up to 2 of these per node, one in sanitary and one in hydraulics, but I can have unlimited patterns in my global database. So I type them in once and I just refer to it. That's what you see here with temporal variation. And then I have my other dry weather flow, which is industrial flow. These are the larger water users. Typically, you can base it on employment, but most of the times I think it's probably based on water use. So you get the water use data from the community and you look at it and you say, okay, well, here's what our water use is for this industry, and we adjust it a bit to think about, well, how much of it is consumptive in the process and how much actually does come out. So for example, if it's a canning plant, well, maybe, only 75% of the water that comes in actually comes out, or maybe even it's less. Well, let's take a little break here from our PowerPoint and let's go to and look at our a model. And I have a very simple model set up here for us to look at today. This is a sewer system, and I have brought in data in a number of ways. So let's start off with looking at our first node. I brought in a constant inflow of 0.01 CFS. That is representing my dry weather infiltration. That's the water that I believe is getting in constantly at all times, regardless of the time of the year, into the system. I then have my dry weather flow, and this is what we just looked at before. This happens to be census-based, so I have a usage of 120 gallons per day, an area of 1.4 acres, and a density of 40 people per acre. Peaking factor in this case is 1, and I'm using the diurnal pattern that is really the same one we looked at in the example. So if I look here, I'll see that at 2 in the morning is actually my low time of flow. Just like we talked that 7 was the high, well 2 would be my low point, and it would be 2 o'clock in the morning on Sunday, where I have a multiplier of 0.7. I have seen models where it's been a recreational community where it's reversed. Monday through Friday are lower and Saturday and Sunday are high because it's a recreational community. If I back on out then of my dry weather flow, I have one other piece of flow I brought in, and that's my user inflow. This I chose to represent a water usage in our community. So what happens is for the first shift, I'm using 0.25, so it's not a great deal. For my second shift, I'm using 0.75 CFS, so it's a full operation. For first shift, for second shift, it's one a little bit less, at 0.5, and this continues on down until you get to Saturday and Sunday. At Saturday and Sunday, it's just a maintenance crew in there, so the water usage drops down to 0.15 CFS during that time frame. You can kind of see the plot here, how the flows go up and down through the day, and this would be how you could represent a water using industry. I could also bring in data using gauged inflow at the same time here, and this way I can actually teach SWIM to take data from another source and bring it in. For example, in the Chicago area, a lot of people use a program called HSPF to generate the wet weather flow situations, and then even dry weather, and then they import it and teach SWIM how to read this gauged inflow. So at each one of these nodes, I have a different dry weather flow pattern. This case, it's still 120 and a density of 40. So, but they are different in places. And I ran this already. It's just a real nice little sewer system. So let me do a long section just to show you what it looks like. So from the beginning to the end, and I'm going to use our dynamic section view to look at this, where I can see both the impact in the long section, and I can also see how the patterns varied and what's happening in the pipe. You can see that during dry weather flow, I'm getting up to maybe about 50% here in this pipe, but for the most part, not a lot. Just a little bit of information on this view. This pipe, the first pipe, is this graphic of the sewer and this hydrograph. So whenever you look at this, so for example, the last one would be the last one in the list, so you can get an idea of what they're looking like. If I go into pipe 50 here and I look at this in results, we can see the pattern that's been expressed through here. If I actually go into the first pipe, you can see something completely different. Here I can see the impact of the water user is very, very strong. You can see that it's pretty much flat and dropping off. But as I move my way downstream, it becomes less and less. And as I get down 3/4 of the way through the system, I can see that now I'm picking up a very nice pattern, and the volume of water from that first manhole where the water user is no longer as big of a factor as it was in the upstream reaches of it. Well, let's go back now to our PowerPoint and move on, and let's talk about the inflow and infiltration. Now, this is what I'm showing you here in this graphic is actually a sanitary sewer. As it says here, this is from Victoria, I believe, Canada. A nice graphic. And you can see what I mentioned earlier. Infiltration gets in through cracks, through joints, through manhole that are damaged somehow. But we don't get as much water. But in combined sewers, then it enters in inlets and direct connections such as roof drains, those types of things. So what I'd like to do is to keep moving forward here and talk a little bit about the storm components of our model. Lots of different ways to bring in data. I did like I did in the dry weather model. I can put a constant inflow for infiltration work. I can create my own runoff pattern, which, as I mentioned earlier, like HSPF does, where we take it, we create the water, and then we import the data. I can also bring in the water through any of the 14 methods that we have in the software. And I can use our groundwater for seasonal or very slow response. And we can also mention, which Nicole did in her introduction, the RTK method. We're going to look at that a little bit more. We also have one other way that I at least want to mention. Back when I first started doing modeling, we did most of our models with the gallons per inch mile day weighting factor, which is good for design or capacity analysis, but it is not good for a full long-term simulation because it's just set up for a one-time event. So here's the RTK method, and the RTK method is basically 3 unit hydrographs, a triangular, that you put in the data. So the R is the fraction of the rainfall, the T is the time to hydrograph, and the K is the ratio of base time to peak time. Notice that I can put in monthly variations. Seasonal, I could turn on just December, January, and February, and then April, March, April, May, June. I mean, I could run this in seasonal, or I can run the whole thing, and I can bring in initial abstraction data as well as initial storage and a recovery rate, and then I pick a rainstorm that I wish to use. And you can get an idea of how it looks over here on the side, where on the lower right side where you can see the flow. The dark blue hydrograph is the peak hydrograph with the combination of the rapid, intermediate, and long term. And this is what a sanitary sewer model might look like in results. We can see that our average flow or our peak flow is about, dry weather is about, what, 1.7, 1.8. But during the wet weather storm event, we end up with 4.2. And that's fairly typical. Where you look at that, and we've got 4.2 divided by 1.7, a peaking factor of 2.5. Very commonly used term in sanitary sewer models is a peaking factor. So wet weather to dry weather peaks are about 2.5 in this case. But when we go to a combined sewer, you get an idea of the difference. It becomes significantly higher. We have, 40 divided by 1.7 again. It's a peaking factor of almost 24. And that's what you expect to see in a combined sewer. And that's why many modelers won't even include, or will include a constant flow down at the bottom here for the dry weather flow, because it's such a small impact that is it really necessary to develop all those flows. That's something that you will have to decide on your own as an engineer. Is it important to show the pattern and show that that's in there, or a straight line, or not anything at all? So I'll leave that to you to decide. And what I want to do now is to jump back to XPSwim. And I'm going to close this model and open up another one from my recent files that I've done, which is the same model, but this time this is a sanitary model with impact flow coming in. So if I go to runoff and I go to any one of my nodes here, I'm going to go to the upstream node again. Notice that I have the same area, 1.4 acres, as I had for my drainage area for my dry weather flow. That's because in a dry weather model, we are typically picking up the same thing. We're going to get water in from the foundation drains. We're going to get water in from the lateral, water in, from everything that's tributary to that particular pipe. Notice, though, that we use an extremely small percent impervious because we are trying to physically model something that occurs very complexly in the field. I mean, we've got water getting in from all these different areas, like we mentioned, in the pipe cracks, etc. And we want to somehow figure out a way to deal with that. So we put in a very small, and we do this for all of these. And finally, if I look at manhole 50 here, or pipe 50 again, you can see that we have a peak flow of 6.4 this time in this example. So it's a little different than the one we looked at, but you can see the rainfall events I didn't show you that. I should really show you that quickly. So let me go in and show you the rainfall that we're using. This is an actual rainfall event that occurred in Lexington, Kentucky. This is June 18th, 1992. The only difference is it was such a large event, I used only 50% of the rainfall. So in this case, I had 4.99, let's just say 5. Well, by using a multiplier here of 0.5, I was able to change this down to a rainfall of 2, which more accurately represented what was going on in the field. And so that's how I bring in water. Now in this one, notice that I didn't use 2 areas. I just used 1. I have just an area that encompasses the entire drainage area. And if I look at this in a long section, once again, we can see that we had some flows, but we didn't get anything, you know, the flow that was about half full now is almost full, this pipe right here, but we didn't get any surcharging going on. So in terms of modeling, we're probably in pretty good shape for this model. But I've got another model that is set up to be a sanitary one. So let me close, not a sanitary, but a combined one. So let me close that one and open up the combined sewer one. In this one, I took this a little bit further because I wanted to show you what the impacts would be if I had basements in the area. So let's start off by going to runoff here. I'm using the same rainfall, 50% of the 5 inches, so 2.5 inches. But the difference is that in this case, I'm using a percent impervious of 2%. One of the key things I need to mention here is that in SWIM, the percent impervious is the directly connected percent impervious, not the full percent impervious. So for example, roofs that are hooked up, that aren't connected directly to the sewer would not be directly connected impervious because it's not hooked up that way, which is why oftentimes you would have 2 pieces of data here, you know, maybe 0.8 or 0.9 here and 0.6 over here, and this would be you know, your roof drain, and then I can use LID information once again to move water, flow redirections. If you're interested in the low impact development, I encourage you to go to our website and look at a presentation that Colby did a few months ago regarding low impact development and how the flow redirection all works. I'm not going to spend any time on that other to mention that that's one of the things that we can do in combined sewers, is to use that as an example and to help. So I have 2 different runs. One is with storage and one is without. Let's look at them together and see what we come up with. And I want to look at, instead of flow, I want to look at an elevation. So if I look at manhole MR49 and I review results, I will see that when I had storage, I had a peak elevation here of 195.5, but when I had no storage, it was 2.5 feet higher, up to 198, almost 3 feet higher. So you can get an idea that, and that's what oftentimes happens in real life, is that the water gets stored in basements along the way, which is one of my little goofball terms I like to use, is basement storage, which obviously is not, well, not good. And we end up with people talking about you know, that actually becoming a CSO now in the future, in which case you know, because it's leaving the system technically. And if I look at peak flows through here, I can see the same thing. I get a very nice reduction of flow when the water gets stored in the basements and comes out later and slower. So I just wanted to throw that in. And what I did with this, just to give you an idea of how I modeled the basements, is I put a node in each storage facility in each node, and I just assumed, for the sake of this operation today, that we would have a 15 by 45 foot long basement, and so I said that they sit somewhere between 5 and 6 feet above the bottom of the pipe, so they're not completely deep, not as deep as they could be, because this is a 10-foot deep area. of sewers. And so this 0.31 is simply a multiplication of 20 homes in the block, 10 on each side, and the 15 by 45 foot basement converted to acres. And so that's how I did it. And the reason I applied it, built it up here a little bit is because some of them obviously are going to be a bit lower, some are going to be a bit higher, which is why you see my storage dipping down a bit as we start approaching the ground. And then I just assumed for all of it that there would be a 1 foot storage available in the ground. If I look at this, and I want to look at my no storage one first, in a long section, this time I'm not going to use the dynamic section view. I'm just going to use dynamic long section. You can see that we had some spots where we ended up with water above the ground. And that's where the magenta line you see exceeded the rim elevation. So for example, right here and right here, let me see if we can find that and stop it for just a second. Well, it's easier to find it if I use the dynamic section views, because dynamic section views shows me the hydrographs. So it is a bit easier to find it, so let me do that. And now if I play this, you can see how the water will come up on the third day here. So as I'm waiting for this to occur, just a reminder again on the hydrology information is that normally on a combined sewer system I would have used two unique patterns to reflect the roofs and the rest of the basin. Let me pause this for a second. One of the things I can do to help figure out where I'm at is I can maximize this. And I can see that I'm still a ways away, so let me drag this a little bit further and see if we can get this here. And we're also looking at every minute, so that also slows it down. But you can get an idea by the magenta line here that we did have flooding occurring at least at 1, 2, 3, 4, 5, 6, maybe 7 nodes. And to confirm that, I could go to the output file. And I'll go to the output file of CSO storage, no storage, and look at table E20, which will show me that I had some pretty large surcharge times. But I don't see any flooding times here. With that, what I want to do is go back to our PowerPoint again and look at a few more things. We've already kind of looked at the results a bit, but these are the different results that we can look at. The grade line, the water surface elevation, velocities, flow, and volumes. Those are the key elements that we look at when we look at results. You've seen this already. Here's an example where you are getting flooding going on. The squiggly lines determine that. And here's an output table. I urge you who use XP Swim to spend some time and look at the output tables, because there's a lot of very good information in there, and figure out what tables really define the information that you're interested in and wanting to learn about. And I also need to spend just a minute or two on calibration, because whenever you do a wet weather model, be it a sanitary sewer model or a combined sewer model, we end up doing what we call model calibration. And basically what we're trying to do is to take the rainfall record that we have, along with SCADA data, which is your flow metering data, etc., and an experienced application of our software, and come up with what we call a reliable model. And we approach that by doing dry weather flows and then wet weather flows. And I listed here using calibration and validation. Another way to do it is to run a longer term simulation and calibrate it that way as well. So the first step is dry weather flows. This is a model from Champaign, Illinois. This is a sanitary sewer model, not a combined, even though it reacts almost like a combined in the fact that it's fairly big reactions to it. And so the first thing we did was to calibrate in the July-August time frame here and to make sure that we were matching our flow metering data very closely. Then we start looking at the wet weather flows, which is the direct inflow, the rainfall dependent infiltration, and the combined of those two to get a response here. And when we did that, that's what we came up with is what you see here. We have the rainfall data up on top, the flow data, the blue is the metered, the green is the modeled. And you can see that we were good in places. At the beginning here, we were pretty good. Oh, I also wanted to point out one other thing on this previous slide. Notice that at the start of the storm event, at the start of our model in the metering data was elevated. That means that we had infiltration going on and groundwater coming in. So when we did this model, we had to go ahead and look at the infiltration coming in, which is a little bit harder to do with the RTK method than it is with the simple swim runoff approach. But you can see that we're able to match this. Didn't do as well here, but the meter also malfunctioned, went to 0, so I really question what the meter responses is because we match these peaks reasonably well, these peaks reasonably well. Now, obviously, this peak too, again, I start looking at, well, what occurred, but that we matched a number of other peaks quite well, and this almost seems like, you know, there may have been some kind of a constriction in the pipe causing not necessarily a backflow, but the water couldn't get out as quickly as it should have in the model versus real world. And this one here is kind of strange, but when you look at it close, you actually find out that this peak storm event here, the rain actually occurred up here a week earlier. So I don't know what's happened. Perhaps I didn't know where the flow meter was compared to the rain meter, so maybe the rain meter was in a different basin, which would explain that. A minute now on alternative solutions. We have partial or complete sewer separation. Personally, I am a little concerned about that because I think in the next years we will see stormwater treatment, and I'm worried that if we were to recommend, you know, separation, that we end up telling our client, well, yeah, but now you have to do stormwater treatment in the future. So just something to keep in the back of your mind as you're looking at it. Storage can be used. These are both pictures from the village of Skokie, and this is a basin that was built to store water during a storm event. And in the case of Skokie, they chose to put water on the street because their sewer system was so undersized, and basically communicated with the residents saying, well, where would you like the water, on the streets or in your basement? And it was well received in the city. So this is what I call ponding, not flooding, because it's meant to be there. And you can see the pavement is still wet. The rain had just quit. This will be dry in about an hour. We have the deep tunnel that we looked at earlier as another option. And we also have green infrastructure. There is a lot going on today in the field. Give you an idea, the city of Kansas City is working with EPA right now on a demonstration project where they are looking at installing 10,000 rain gardens and basically using green infrastructure instead of gray infrastructure. So by doing this, establishing and reducing the amount of sewer improvements they'll have to do. Source control, which is what can be also a lot of times referred to as low impact development stuff. I'm referring it to what's kind of what Skokie did, where you control the water at the source and you only let into the combined sewer system what the sewer can handle. But most likely it's going to be some kind of a combination of all of the above that you're going to end up doing to make this work for a combined sewer community. And since I mentioned green infrastructure, I did want to show you just that there are site infrastructure that you can do, green roofs, etc., rain gardens, and there are also neighborhood, which is green streets and highways, pervious pavement, etc. And finally, there are watershed approaches, riparian buffers, etc. Again, I would urge you, if you have more interest in low impact development, to look at Colby's presentation in the previous XP Live. And finally, the last thing I wanted to show you was a solution from Skokie. The reason Skokie is so near and dear to my heart is I've worked 14 years on it. I'm still working on it. It's been almost 20 years now. And to give you an idea, they had water back up in their basements. They stored water on the street, underground storage, and by controlling it at the source, releasing the water at a controlled rate to not surcharge the sewer system. And once again, I have an example of actually the Skokie project for you. This was modeled in originally in a DOS version, because this was done back in the 80s, started back in the 80s, and have converted this now to XP Swim. In this particular example, we did not use the two methods, because back when the model was built, this wasn't available to us to do. So in this case, this sub-basin here has 2.7 acres with a percent impervious of 25%. Again, remember that is directly connected, percent impervious. So most of the roof drains here by ordinance have to be discharged to the grass. And this particular example that I'm looking at here is a storm event that occurred on September 13th. And if we look at it, you can see that it is a total of 6.88 acres over about 21 hours, which is approximately a 50-year storm event for that part of Chicago, or that part of Illinois. And why I wanted to show you this was, first of all, that in this case, we didn't break it into areas, but the modeling techniques used were kind of different. The blue lines are the combined sewer system. The green lines are the street systems. So for example, if I look at this across the street here, come on, there we go. And I look at this in the dynamic section view again, you can see that I have street storage occurring in there, and I also have, we call them berms. I modeled them as a weir. So here's an example of a weir, and if I play this, you'll see the water actually come over the top of the weir. You can see that water flows both ways. You've got a negative flow here and a positive flow. So as the water comes up and goes over the berms, the water gets in. Whenever you see a deep area like this, what's going on there is that's a catch basin, and the water is going from the catch basin to the combined sewer. So here you can see right now that it is overtopping the berm, and blue is over the top of the little berm there. So it is where it is overtopping it, and water is being stored in the street. Won't go into all the depth rules and stuff on this because it's just not the place for it, but I just wanted to show you this, and I'll stop this. And then the red lines are restrictors. So what these are this is my street, this is my sewer. So in this case, I modeled my berms, or my restrictors, as a orifice, and I use that as a special because it works easier to use this as a rating curve. So what I did is I calculated, based on depth, what my flow would be through this orifice, restrictor 627, and you can see that as it gets deep. So one of the advantages is as you get deeper, you can see that the flow doesn't go up as much. So you hit about 8 feet, you're at the surface. Well, 2 feet above that, you're only up another 6/100ths of a CFS. So in this case, I'm using essentially an orifice, but I chose to use it as a rating curve simply because a rating curve runs faster than an orifice does. So it made it a little bit quicker. And here you can see my berm. And if I double click on that and edit the data, you can see it's a weir. And it has a crown and a crest. So the crest here is 596.8, and the water at that point will flow, and water can flow either way to or from this berm as the water gets deeper. In fact, if we look at the graphic here, you can see that actually the peak flow occurs backwards. So the largest flow goes from this node over to this way rather than the other way through that. And if I look at the a long section view of the combined sewer, through here, you can see that this particular storm event didn't fill up the sewer. It's a very small part of the sewer system in Skokie, the smallest basin that they have. I have one other model that I'd like to show you, and that is a model that's being done right now for the city or the village of Lincolnwood. And this particular model, I wanted to show you this one because here is an example of, notice in the Skokie one, we used two unique links for the pipes and the sewers. That's because each one of these green links has a cross-section that was surveyed for each piece of these streets. So there were a lot of survey cross-sections taken. Well, in Lincolnwood, we were able to use a 10, and we were able to therefore come up with a unique drawing or a unique cross-section for each row. Let's start off by looking at runoff. If I look at manhole 53 here, I can see that here is an example of what I was referring to. We have a acre of 6.5 acres, or area of 6.5 acres, 46% impervious, and what we've got going there is that water is going into, this is the water draining from everything but the roofs. And notice that what we did do also is, for the most part, we said, okay, we're going to take that pervious runoff into impervious before it discharges. However, on our roofs, it's reversed. We're going to take and we're going to drain it to the same node, to subcatchment 1, and we're going to drain it impervious to pervious. So it's just another way of approaching modeling here in the business. But I also wanted to show you that in this case, for the streets, we modeled them as a pipe and a conduit, which is dual, what we call dual drainage in XP Swim. And so if I look at the street here, I look at my cross-section. This cross-section was actually measured from the tin that the village of Lincolnwood had. So we didn't go out and survey this. We actually measured this, drew it right from the tin. So that saved us a lot of effort in survey. And we also applied inlet capacity to each one of these to control the amount of water that goes into the sewer versus what stays on the street. And based on the number of catch basins in each area, each one of these has a unique curve. So if I edit this one, you can see, well, this one doesn't. Of course, I picked one that didn't have one. Here we go. You can see how much the flow is at the depth and what the captured flow would be. So just again, another way of showing you what's going on with this and a different way of modeling. And with that, we will wrap this up. Thank you for attending.